Hello, everyone. My name is Luna Hasani, and I'm a PhD student at Georgia Tech. Thank you for joining my talk. Today, I will be describing how to predict heat of hydration of cementitious systems using machine learning and how to use these predictions for mass concrete modeling. So first, I will start by giving a brief definition of what mass concrete is, and then how to perform thermal modeling of mass concrete. After that, I will discuss how I'm using my results, how I'm performing machine learning in order to predict heat of hydration of cementitious systems, and finally, how I'm using my results in order to perform thermal modeling of mass concrete. So mass concrete is a structural element where a combination of the mixture design, the element geometry, the boundary conditions, and the environmental conditions contribute to large temperature rises in the concrete element. And these large temperature rises could result in durability issues if not controlled. Now, the maximum temperature that a concrete element could reach can be divided into three main components. The first one is the placement temperature of the concrete. Then we have the adiabatic temperature rise of the concrete. And finally, we have any temperature losses with the environment. The focus of today's talk is how to find the adiabatic temperature rise, which is the maximum theoretical temperature that a concrete can reach. And it is a function of the heat of hydration of the cementitious system that we're using in our concrete. The methodology I have explored in order to find the adiabatic temperature rise makes use of isothermal calorimetry in order to find the heat of hydration of cementitious systems at constant temperatures. And as you can see in the figure at the bottom here, that I'm finding the relationship between the heat of hydration of the cementitious system and the rate of heat of hydration in the vertical axis as a function of multiple temperatures. These temperatures were selected to be representative of the range of temperatures that are expected to take place in the mass concrete cores. Now, after finding this relationship, I need to consider how to go from this figure here to finding the adiabatic temperature rise. One thing to note is that this figure has the relationship between the cumulative heat and the rate of heat release at isothermal temperatures, which means constant temperatures. This is not the case in mass concrete, where temperature is developing with time. So what we can do is come in here in this figure and find two of these three values, two of these three axes, and use the values in order to find the third one and find the adiabatic relationships. So for concrete, I could easily find the heat of hydration based on the characteristics of the cementitious paste. And I could also easily find the temperature development under adiabatic conditions when I have information on the heat capacity of this concrete. So now that I have these two for specific concrete, I could come in the figure and find a unique value of the rate of heat release P for any two values of H and T. After finding all of this information that I need, I could come in and plot the information that I found, which is what you see in the dashed black line. So this is the rate of heat release, the cumulative heat of hydration, and the adiabatic temperature rise for a certain concrete, and as I said, under adiabatic conditions. But there's one dimension still missing, which is time. From some more data processing, I could, and some differential relationships between the cumulative heat and the rate of heat release, I could find time. And finally, I could plot any of the information in these three axes with respect to the time that I found. And this figure here is showing the adiabatic temperature rise of the concrete. Now, the purpose of this slide is not to describe the method in detail, it's just to show that I could start from finding the heat of hydration of the cementitious paste at different temperatures and go from there to finding the adiabatic temperature rise of the concrete. After finding the adiabatic temperature rise, I could use it in finite element simulation in order to find the final internal temperatures in mass concrete structures. So now my research question was, how could I find the heat of hydration in order to perform that calculation that I've just shown without performing isothermal calorimetry experiments? The first approach that I explored was using kinetic models to predict heat of hydration. And using kinetic models, we could actually explain early age hydration in the first 72 hours using mainly halide reaction. And the halide reaction could be divided into three main phases, and each one of these phases could be described using a different controlling mechanism, and each one has its own model. So we need to consider all of these models in order to get the heat evolution rate, which you see in the image to the left. This process could be more complicated if you would like to include the hydration of C3A plus gypsum. And it could be even more complicated if we wanted to include the effect of using SCMs and admixtures on the rate of heat evolution. In addition to this complexity, the kinetic models may not be generalizable, so they may be able to fit some of the cementitious systems that were used to validate and calibrate these models, but they may not generalize to a wide variety of cementitious systems that I'm interested in. So for these two reasons, the use of kinetic models was found not suitable for the application that I was interested in. Therefore, I looked into the use of machine learning in order to predict heat of hydration curves. I have collected 407 cumulative heat of hydration histories. I have performed some of these experiments myself, and the other experiments I have collected from different universities. And the features that I included in my model were ones based on the literature review, were found to affect early age hydration mostly. So the ones that I included are some information on the oxide analysis of the cement, some information on the mixture design, the water to solids ratio, and also, of course, some supplementary cementitious materials. Here I used fly ash, slag, and limestone. And also I had to include time because heat of hydration is a time series, and temperature because I was interested in the effect of temperature on heat of hydration. The machine learning algorithm that I used is Gaussian process regression. And this is a probabilistic approach. In Gaussian process regression, well, in order to understand the process, let's consider the relationship here of y is equal a function of x. And we know, for example, for linear regression, the function would look something similar to this. So y would be equal to a constant times x plus another constant. Now, for any unique value of x, we could find a unique value of y in linear regression. In GPR, however, what we do is find a distribution of values for any input x. So if you look at the image to the right over there, so for an input y1 is equal to n, we could actually find a distribution of y2 values. And this distribution has a certain mean and a covariance. The covariance function of the distribution is a function of what is known as a kernel. And in Gaussian process regression, kernels perform pattern analysis. They find similarity between different data points. So for example, let's say we have points x1 and x2 and are similar. And then we find that x1 has an output y1 and x2 has an output y2, and the two outputs are also similar. Now let's say that we have another extra point x star, and we could establish that x star is similar to x1 and x2. Therefore, we would expect that y star as an output would be equal to or similar to y1 and y2. And an example of what a kernel, nonlinear kernel looks like is shown here in this equation. So I have trained my model using GPR, and I have validated my model as well. And I will, in the next slide, I will show some results. These results here are shown for different cementitious systems. So I have some Portland cement mixes, class F fly ash and blast furnace slag, and finally limestone cement. And I'm showing these predictions at different test temperatures. The observed heat of hydration using isothermal calorimetry, the experimental value is in the solid blue line, and the blue circles are the prediction. So we can see for all of the systems that the prediction is matching very well with the experimental heat of hydration. Now the gray lines are showing the upper and lower confidence limit for my predictions, because as I've said, this is a probabilistic approach. It could provide a 95% confidence interval for the prediction, and this is what I'm showing here. I also wanted to look at the results another way. I wanted to see if the residual between the observed heat of hydration and the predicted heat of hydration changes with time. And here I'm looking only at the first 72 hours. I know these are lots of data points, but let's just think about the evolution of these data points with time. Is the error increasing or decreasing? And we can see that the error is actually stable for all of the different mixes with time. There's a slight deviation here that we experience in the first 10 hours, but then this deviation tapers off for the remaining of the period. Some mixes are experiencing higher residuals than others, especially those containing class C fly ash, which could mean that we need more data points in order to capture the behavior of systems with class C fly ash. Now, in order to assess the stability of the prediction model, I have performed 200 iterations. I have trained the model using 200 iterations, and I was able to obtain mean values for the model assessment measures. So here the measures I was interested in are R squared, root mean square error, and the mean absolute error. And we can see that for the 200 iterations, my average R squared value was, for example, 93%, which is pretty good. So now after training the model, I was interested to see how it would perform if we upscale these values and use them for mass concrete application. For this reason, I used a mid-scale experiment, which we performed at the lab at Georgia Tech. It is a mass concrete mid-scale experiment, and the mixture design of this experiment contained 25% fly ash replacement. The chemical and physical characteristics of the mixture design are shown in the table here, and these are only the values which are relevant to my GPR model. I've predicted the heat of hydration curves at constant temperatures for this mixture design using my GPR model, and you can see here the comparison between the observed heat of hydration and the predicted heat of hydration for this mixture design at various temperatures ranging between 23 Celsius and 60 degrees Celsius. After finding the heat of hydration, I could perform the same methodology that I showed in the second slide. And I could go from here to finding the adiabatic temperature rise and finally use this adiabatic temperature rise in finite element simulation, which is what I did. This here on the left is a schematic of the experiment, and I'm showing temperatures at sensor location TS2. And in this figure to the right, we can see the results from the finite element modeling using the heat of hydration curves that I predicted from my GPR model. The red curve is the sensor temperature, and the shaded gray area is the confidence interval of my prediction. And we can see here that at around 20 hours, the maximum temperature of the concrete read by the sensors could be perfectly matched using the GPR confidence interval. And not only that, but also the time at which the maximum temperature occurs could actually also be captured accurately. We do see some deviation after the first 24 hours. This is a slight deviation of around 3 degrees Celsius. This is not due to the heat of hydration modeling, but it's more due to the modeling of the boundary conditions of my experiment using the finite element software. But generally, we're very happy with the results. So to conclude, I have shown here how we could use machine learning in order to predict the heat of hydration of different cementitious systems, and how we could use this heat of hydration in finite element modeling in order to perform accurate thermal prediction of mass concrete structures. And thank you very much, and I will take any questions.